Hello, Physical Science. This is Mr. B, and we're going to continue on with Section 2 of Chapter 13, and that's going to be forces and pressure in fluids. So we just looked at fluid pressure last time about how it changes with depth and over the area that it's distributed over and things like that. So now we're going to take a look at how forces actually can apply to those changes in pressure. So as always, we have our little example to start here. So it says the fast-moving stream of air from the blow dryer creates a column of low pressure air. And so the table tennis or ping pong ball is suspended in an area of low pressure. So the actual reason, again, we've all could probably predict what's going on here. Again, we can feel the air moving out of the blow dryer, and maybe we just think that force is pushing it up. But really what is happening is that air is actually of lower pressure because of the speed, and so therefore the ball is trapped in that area of low pressure. So that will make more sense here in a little bit about why low pressure air might cause that to happen. So that's just our example here to get us kind of thinking about this chapter. And so now Pascal's principle, so we talked about the SI unit of pressure being a Pascal. So how does that describe transmission of pressure through a fluid? And again, a fluid can be a liquid or a gas. So what is stated in Pascal's principle is a change in pressure at any point in a fluid is transmitted equally in all directions throughout the fluid. So we have a very good example right here. So we have a bottle filled up with probably either soda or water, probably maybe even ginger ale in that one. So it says the forces against the walls of the container are equal at any or at a given depth. So if you look in picture A right here, all the forces, remember force is a vector, so the magnitude of the force can be represented by the length of the line or the length of the vector. All these vectors are of equal length. So the forces exerted against the wall of the container are equal at a given depth. And if you notice the ones down, actually kind of scratch that here, these ones are all equal because they're all at the same depth. These two are equal because they're at the same depth. These ones are equal because they're at the same depth. These ones are equal because they're at the same depth. And then these three are equal because they are all at the same depth as well. So again, the pressure is equal depending on the depth. Remember we said that last time. So when we squeeze the bottle here in picture B, the pressure is transmitted equally throughout the fluid. So if you've noticed now, all of our lines have increased by pretty much the same magnitude depending on what depth they're at. So this line and this line, now the force is greater because the pressure from the outside causes a greater pressure on the inside, but it's not like it's an unequal distribution of the force. It's like the squeezing is happening right here, but that's not where the greatest force is. The force is distributed equally throughout the entire fluid. So that is what Pascal's principle says. A change in pressure at any point in the fluid, so here's our change in pressure, is right at this point right here. You see the two big red lines, that's our change in pressure. So if it's transmitted at any point in the fluid, it's equally and unchanged in all directions. So our pressure increased equally in every single direction. It's not like right here was our greatest increase. All of them increased in the same way throughout the fluid. So that is Pascal's principle. And then, again, that's what I just said. I just explained all of this right here. So for our next one, some way that this can kind of relate to a real-life example is something called a hydraulic system. So a hydraulic system, if you're familiar with cars and trucks, you might know what this is a device that uses pressurized fluids acting on pistons of different sizes to change a force. So it says here, and this will make more sense here once we see our little picture in the next one. It says, in a hydraulic lift system, an increased output force is produced because a constant fluid pressure is exerted on the larger area of the output piston. And again, they kind of did this a little bit backwards, so it'll make more sense here in a second. So the truck uses hydraulic-powered struts to lift its load. So right here, the reason why, again, this truck obviously doesn't just drive around like this all the time. If they ever need to unload the cargo that's in here, they use these hydraulic lifts. And so the larger area of the output piston produces the increased force. So, and again, kind of going even backwards. So I'm going to go one more slide and then we'll come back to make this all make sense. So it says when an input force is applied to the small piston in a hydraulic system, the piston pushes against the fluid sealed in the system. So we're going to go back to this one. So this is right here. Our input force is this tiny little red line down here, and this little cylinder right here is our input piston, our smaller one. And so our how this truck works is something applies a force to this piston right here. The piston then is going to apply a force to this fluid. So that's our first step, and this fluid is trapped, so it's not going anywhere. So it applies a force onto that fluid, and then the pressure produced by the small piston is transmitted through the fluid to the large piston. So then the pressure goes from here to it starts in the small piston, goes to the fluid, and then here's our larger piston up here. And the pressure on both pistons is the same, but because the output pressure acts on a much larger area, the output force is going to be larger. So because they spread it out, because it acts over larger, now this piston is going to be able to push much harder and provide a greater output force than what was actually put into it. So hydraulic systems are very effective, and they harness fluid pressure in order to kind of move things that are probably they try to move things by using a smaller input force to generate a greater output force. So it's kind of cool how hydraulic systems work, and one of your extra credit projects is actually to make your own hydraulic system. So hopefully someone could actually carry that assignment out and see what, show that to everyone. So that is how fluid pressure, again kind of working with Pascal's principle as well, because again it exerts it equally throughout the entire piston there. And so our next principle we're going to look at is a guy by the last name of Bernoulli. And his has to do with air pressure, and actually another good real-life example with flight we're going to see here in a little bit. So it's going to say, how is the speed of a fluid related to pressure within the fluid? According to Bernoulli's principle, so that's our big question, and according to his principle, he says as the speed of the fluid increases, the pressure within the fluid decreases. So that is a huge thing, and this kind of goes back to our hairdryer example at the beginning. When you increase the speed of a fluid, the pressure within it is going to decrease. And there's a very simple experiment you can do with this. If I can get it to go, okay. So a very simple experiment, you could do this right now if you have a sheet of paper, is you hold it by the top of its corners, and you position the paper directly in front of your mouth. So hold the sheet of paper, hold it right by your mouth, and then you just blow over the top of the surface of the paper, and the far end of the paper actually lifts upward. You would think that maybe you're blowing the air, so the force from you blowing the air would push the paper downward. It's going to do the opposite. The far end of the paper is going to lift upward. And the reason why that happens is because as the air blows across the top of the paper, the pressure exerted by the air decreases. So it's faster. Again, we just said, as the speed of a fluid increases, the pressure within the fluid decreases. So you blow across the top of the paper, that means the pressure now on top of the paper is lower, so the pressure below is higher. So the motionless air below the paper is going to exert a greater pressure, and the difference in pressure forces the paper upward. So we're going to talk about this more in class, and we'll do it then. That's a really good illustration of how Bernoulli's principle works. And this explains the ability of birds and airplanes to fly as well. So not just as simple as paper moving up in the air, but in order for flight to occur, Bernoulli's principle comes into play. So air traveling over the top of an airplane wing moves faster than the air underneath, and then the pressure between the top and the bottom of the wing creates an upward force known as lift. So definitely make sure you write that down. So again, that's just kind of an interesting real-life example again of forces and fluids. Again, there's a lot of interesting real-life examples in this chapter. It's short, but it is very informative. So again, right here, air flowing over the top of the wing is diverted up over the wing's curved surface. So airplane wings are curved in order to maximize Bernoulli's principle to get the faster air moving over the top, and then to create lift underneath of the wings. And then birds do the same thing as an airplane does, but birds can flap their wing to produce the forward movement and some lift, whereas the forward movement and lift is motorized here for the airplane. And then a downward force created by the spoiler of a race car actually pushes the tire down onto the road, giving the car better traction. So again, a lot of real-life examples present here with Bernoulli's principle and pressure. And then our last real-life example, which you wouldn't think is actually a spray bottle. So pressure differences between the solution chamber and the moving stream of water draw the solution into the stream. So water moves through the sprayer at a high speed, so therefore it's going to be low pressure. And then the concentrated fertilizer is going to move up there, and then the water and fertilizer mix, and then the mixture sprays out. So because there's less pressure here, things tend to move from an area of high pressure to low pressure, and then that creates, again, something simple as a spray bottle works through Bernoulli's principle. So again, I know this one went a little bit longer, but again, a lot of interesting information within this chapter. So that's it for this video. Let me know if you have any questions.